Black holes are this ultimate cosmic paradox. I mean, they're regions of space-time so incredibly dense that their gravity is inescapable. By definition, that makes them totally, completely invisible. So how in the world do we study them? All right, let's dive in, because it turns out the key to seeing the unseeable lies right there at the very edge of darkness. So back in 2019, the Event Horizon Telescope collaboration gave us this, our first direct look at a black hole silhouette. And this isn't some artist's drawing. This is the real deal, real data from the heart of the M87 galaxy. Now, what you're seeing isn't the black hole itself. It's this superheated, glowing gas that's swirling around it. And it reveals this incredible signature, a dark central region, what we call the shadow, surrounded by this brilliant, brilliant ring. Which, of course, leads to the big question, right? If a black hole is a one-way street where nothing gets out, how are we getting this postcard back? What is this light, and what's the physical structure creating this amazing ring? Well, the answer takes us to the very brink of the abyss. To really get what we're looking at, we first have to understand the geography of the space just outside a black hole. And let me tell you, it's a region governed by some of the most extreme physics in the entire universe. The most famous feature, of course, is the event horizon. Now, this isn't some kind of physical wall, It's a boundary. If you cross it, you are not coming back. That's because the speed you'd need to escape is faster than the speed of light, which is impossible. So no information from inside can ever reach us. This is the edge of that true darkness we see in the shadow. Okay, so this map here kind of lays out the key areas just outside that point of no return. Right at the center, you've got the event horizon. As we move out, we find the innermost stable circular orbit, the ISCO, which is basically the last spot where matter can safely orbit without just falling in. But look, notice that area between them? There's another crucial boundary in there, and that's the key to everything we see. It's called the light ring. This light ring, sometimes called the photon sphere, is the absolute key to understanding these images. It's a place where gravity plays by some seriously bizarre rules. Now, just think about that for a second. Light is supposed to travel in a straight line, right? Unless gravity gets in the way. Well, around a black hole, the warping of space-time is so extreme, it can literally bend the path of light into a perfect closed circle. A photon could get stuck orbiting the black hole forever, trapped by nothing but gravity. This visual here, it shows us exactly what's going on. So imagine a flare of hot gas near the black hole, and it's sending out light in every direction. As you can see, some of those rays just escape, and some fall right in. But the really interesting ones are the photons with just the right trajectory to get caught. They loop around the black hole, sometimes over and over again, before finally getting flung out toward our telescopes. And this isn't just a cool idea. As these lecture notes from Cardoso, Biswas, and Sarkar explain, it's these photons on these critical trajectories that actually populate this region. They get incredibly close to being trapped forever, just skimming the edge of that light ring before they manage to escape. So here's the big takeaway. That bright glowing circle we see in the EHT image is not just any old glowing gas. No, it is the light ring. It's a collection of photons that have taken the most extreme possible paths, lensed and magnified by the black hole's gravity. It defines the very edge of what we can see. But believe it or not, the story doesn't end there. This light ring is responsible for a whole lot more than just a picture. Yeah, so the importance of the light ring doesn't just stop with what we can see. It's also fundamental to how we can hear black holes. And to understand that, we need to switch gears from light waves to a completely different kind of cosmic messenger, gravitational waves. Okay, so picture this. Two black holes spiral into each other and merge. When that happens, they send out these powerful ripples in the very fabric of space-time. Those are gravitational waves. And our detectors, like LIGO, can actually hear these cosmic collisions from billions of light years away. The signal we get shows the two objects getting closer and closer, faster and faster, until, boom, they merge into one. But after that collision, the new, bigger black hole is, well, it's all shaken up. It doesn't just settle down quietly. Instead, it vibrates. Seriously, it's just like striking a bell. It radiates away all that violent energy from the merger in a process we call ringdown. Now, these vibrations, they're not just random noise. They happen at very specific, characteristic frequencies called quasi-normal modes.
And just like a bell has its own unique tone based on its size and shape, a black hole's sound is determined purely by its mass and its spin. We actually call this black hole spectroscopy. We analyze the notes to understand the instrument.
Okay, so this is the moment where it all clicks together. We've got this visual thing, the bright ring of light, and we've got this auditory thing, the gravitational wave ring down. How on earth are they connected?
The answer, believe it or not, is all about the physics of that ring down, and it takes us right back to that same exact spot, the light ring.
All right, let's just walk through this. First, the merger creates a storm of gravitational waves. Then, this radiation floods the space around the new black hole. And just like with light, some of it gets temporarily trapped in the light ring. And here's the key part. The light ring acts like a resonance chamber. It holds on to this energy and then slowly leaks it back out. So what we detect as the ring down signal, those quasi-normal modes, is precisely that trapped radiation being released.
So here's the punchline. This one single structure, the light ring, is the fundamental key to both of our main ways of observing black holes. For imaging, it traps photons from nearby gas, and that creates the bright ring we see with a telescope. For gravitational waves, it traps the waves from a merger, creating the ring-down sound that we hear. It is the unified key to both seeing and hearing these cosmic giants.
And you know what's just absolutely wild? When we measure these things, when we measure the size of the light ring from an image or the frequencies from a ring down, they match the predictions from Einstein's general relativity with stunning precision. I mean, we are directly testing the laws of gravity in the most extreme environment you can possibly imagine. And so far, Einstein is holding up beautifully.
So from painting the edge of a cosmic shadow to basically conducting the final gravitational song of a merger, the light ring is our direct line into the physics of the event horizon. It lets us probe the very fabric of space-time right where it's bent to its absolute limit. And that just leaves us with this one thrilling question: what other secrets is it waiting to show us?